Hello everyone, it's Mark here from XPS, and we've got another look at one of our recent publications. Only this time, instead of it being a research paper, I wanted to look at one of the insight notes that we've been publishing recently. This time we're going to be looking at Coster-Kronig broadening in XPS spin-orbit doublets. So that's what we're going to be looking at here. Recently published in Surface and Interface Analysis. I will stick a link to the paper in the description below. So first, what on earth am I talking about? Well, that seems like a reasonable question. I'm taking it as an assumption that if you are watching this video, you are familiar with spin-orbit coupling as a concept, and you're aware that for a pair of spin-orbit coupling peaks, we typically take the peak width to be equal of the two peaks. Well, as you may have found out, if you've ever tried to analyze certain elements, such as titanium, this is not always the case. Sometimes the higher binding energy peak is slightly wider than the lower binding energy peak, and this is primarily due to something called Coster-Kronig broadening. So there are three major types of broadening in XPS peaks, coming from an X-ray source, in other words, the natural line width of the emission, spectrometer broadening, so broadening due to analyzer resolution, lens imperfections, thermal noise, statistical spread of electron paths, etc. And I will include sample inhomogeneity in this category too. This is effectively an experimental property. Small differences in chemistry of your sample contribute to broader peaks. They have slightly different electronic signals, whether this is due to sample preparation or actual differences in the chemistry of your sample itself. And then the third type of broadening is the intrinsic line width. Now the first two types are very Gaussian in nature. They're all caused by some kind of statistical spread, random fluctuation, which according to the statistical model central limit theorem, all results in a Gaussian type bell curve distribution. Now the third type, however, is a bit different. This results in a Lorentzian type distribution of energy states, as we see on the right hand side here. So our peak width, the full width at half maximum, is the square root of the sum of the squares of the line width of the X-ray, the spectrometer, and the intrinsic components. Now instrument line widths are typically on the order of 0.5 to 1 electron volt, depending on the configuration, if the source is monochromated, etc. And the intrinsic line widths span a pretty large range, so around 0.04 to 4 electron volts. So it is important, as I said earlier, to recall that when we have these spin-orbit doublets in XPS, the peak width is typically the same for the two peaks. Now our core hole lifetime is going to be unaffected by angular momentum and electron spin coupling. So when we model these, we constrain the peaks to have an equal width. So why then do some systems, like this molybdenum 3D spectrum, appear to show different peak widths? Again, this for most cases is down to Coster-Kronig peak broadening. So what is this Coster-Kronig process? Well, first let's have a very quick recap on Auger-Meitner emissions. Auger-Meitner electron release is a final state effect in XPS, where secondary electrons are emitted from an atom, resulting from the creation of a core hole. When we release a photoelectron, our system is in an excited state, and atoms tend to want to exist in as low an energy state as possible. So as a response to this, an electron in a higher orbital drops down to fill this hole and releases some energy in the process. It can do this in one of two ways. One is just by giving this energy out as radiation, so as X-rays, which is the process by which X-ray fluorescence works. This tends to be favoured for deeper core orbitals and heavier elements. But the other way is to transfer that energy to an electron in the same orbital and kick out that electron from the atom with a given kinetic energy. Now the kinetic energy of this electron is going to be equal to the difference in the energy between the two orbitals involved, minus the energy penalty from removing that Auger-Meitner electron. And we can measure these electrons in XPS, and it gives us all kinds of useful information. But that's not really the scope of this video, and we have covered this in various detail in previous videos, so you can find those if you're interested. By contrast, for a Coster-Kronig type emission, when we create this core hole, we actually fill this hole with an electron from the same orbital. If you recall spin-orbit coupling, you'll remember that within a non-symmetrical orbital, so a p, a d, an f orbital, our electrons can exhibit coupling of the electron spin and the angular momentum of the orbital in question, which gives us two energy states, one with a slightly higher energy than the other. Now, this state with slightly higher energy can fill that created core hole and transfer a very small amount of energy, so the energy being the difference between these spin-orbit doublet peaks, to kick out a very weakly bound electron, typically with very low kinetic energy. So what processes do we see? Well, if we recall our Auger nomenclature, this is the nickel LMM region as an example. You'll recall that our Auger name tells us about what transitions are involved. So in this case, we have an L shell as the initial core hole because this is the first letter. We have L2 and L3 possibilities for this core hole, aka the 2p3/2 and 2p1/2 states, which gives us two possibilities for each of the major groups of emission. We then have the LM45M45, which is a 3d electron filling this core hole and emitting another 3d electron. The M23M45, which is a 3p electron relaxing to fill the 2p core hole, kicking out a 3d electron. Finally, we have the LM23M23, which is a 3p electron relaxing, kicking out a 3p electron. In all of these cases, however, we have pretty high kinetic energies for our electrons, since the energy difference between the M shell and the L shell is pretty large. So when our electron relaxes, it's losing quite a fair chunk of energy, and it gives it to this Auger-Meitner electron. So in order to kick out an Auger-Meitner electron, we need a big enough energy gap between the core hole and the relaxing electron to overcome the binding energy of the third electron that we are kicking out. So in the case of our standard Auger emission, that's no problem. If we look at the nickel energy level here for our LMM Auger, we've got around 850 electron volts to play with if we're kicking out one of those M shell electrons. But what if we have a Coster-Kronig type emission? Well, this time instead of an LMM transition, we have an LLM transition, not a large language model. So we create a core hole in our L2 shell, and then we fill it with an L3 electron. Remember, this is the same orbital, or the same shell. These are both 2p electrons split into slightly different energies due to angular momentum coupling. So the energy gap between them is very small. We've got 17.3 electron volts that we can give to an electron to kick it out. And our valence electrons are going to be happy to accept this. 17.3 eV is well above the binding energy of these electrons. But if we look at a similar example, molybdenum, our typical Auger emission is pretty straightforward still. We only have 230 electron volts, but this is plenty to kick out a valence electron. But our Coster-Kronig type emission, the MMN in this case, is a bit trickier. We've only got 3.15 electron volts as our doublet separation between those two energy states. So we can only really kick out valence electrons with binding energy below this. So what does that mean for our spectrum? But if we're filling this core hole that we've created in the L2 or in the M5 with a higher energy electron, so from the L3 or the M5 in either case, what that means is the core hole that we create in the L2 or the M4 is actually going to be shorter lived than the core hole in the L3, which doesn't have this Coster-Kronig process as an additional decay pathway because there's no associated higher energy orbital for this type of transition to occur. So effectively, our higher binding energy peak has got an additional decay pathway, which means it's got a faster decay route, and it means its core hole lifetime is going to be shorter than the higher, the lower binding energy counterpart. Apologies. And if you recall earlier when we spoke about the relationship between core hole lifetime with peak width, this is what gives us this more broadened peak for the higher energy component of some of these spin orbit couplets for our spectrum. We'll say we look at titanium. I've moved on from nickel just to avoid confusion around multiplet splitting, and we can have a bit more of a simplified data set to look at. Our titanium metal has a bit of broadening for this 2p 1/2 state, or the L2 state. The doublet separation for titanium metal is around 6 electron volts, and our VBM is 0. This is a metal, so the VBM is effectively at the Fermi level. That's the valence band maximum, if you're not familiar with the terminology. So we can easily kick out an electron here. Our doublet separation is larger than our VBM, so we have enough energy to overcome the binding energy of these valence electrons. Similarly, if we look at titanium dioxide, we now have a non-conductive system. So our valence band maximum is just going to be sitting a few electron volts above the Fermi. But the doublet separation is still just shy of 6 electron volts. So we can actually overcome this barrier and excite a Coster-Kronig Auger-Meitner electron. So our doublets are still seeing different widths, different full width maximums. If we move on to molybdenum, where we got a smaller doublet separation of only around 3 electron volts, well, this is plenty to excite a weakly bound electron in a conductive system. So here we've got a molybdenum telluride system, and this gives us a broadening of that higher binding energy peak in the doublet. If we then move on to a non-conductive material such as molybdenum trioxide, we've now got a larger VBM to overcome, and this time it's above the energy that we can harvest from this doublet separation, and so this transition is not allowed. It can't happen. So we cannot excite this Coster-Kronig Auger-Meitner electron, and therefore the width of our doublets is now the same, because we've turned off this decay pathway, which means our L2 state is no longer decaying to fill the L3 state, and so the lifetime is going to match that of the L2. So that's where we see this for some systems and not for others. I'd just like to finish off by thanking my co-authors, helped me put this article together. So the Harwell XPS director, Professor Rob Palgrave, my colleague at Harwell, Arthur Graff, the technical director, David Morgan, and the co-director of Harwell XPS, Professor Phil Davies. Thanks to the EBSSC for all the funding, and to the research complex at Harwell for hosting us, hosting our labs. Thanks to all of you for watching, and hopefully we'll be back soon with some more topics. See you soon.